haven't take the attendance, please do so. Okay. All right. I would like to recap back what is actually meant by dimensional analysis. All right. Please look at this video. This is fun and interesting video. Okay. First, I hope you can concentrate on this here. All right. What we have here is this is the cylinder and this is the flow from the left to the right. And then we have the drag force FD. Okay, we have the drag force FD. So this is the professor explained the two person conducting the dimensionless analysis for their experiment. All right, the first person worked at this company. Okay, that means one person, all right, person A conduct the test at this lab. Wait, yeah, there's someone coming in. So basically, this professor explained there is one person A named A conducting the experiments of the fluid flow across this cylinder. Right? They have a few variable affecting variables of the drag force here, FD. So they investigate that drag force is the function of diameter, velocity, the density F mu.
Sir, we cannot hear the video, sir.
Oh, okay. Seriously? Okay, thank you for. All right, let me change the setting first. Speaker, video. Okay, it's okay. Let me explain. Okay, this is how one person conducting the experiments of, we call here as a drag force FD versus the diameter. So they conduct the experiments of different velocity. All right. So they conduct at different velocity. So, and then the velocity that they conduct, for example, like 1 meter, 2 meter, 3 meter, 4 meter, 5 meter. All right, different velocity will have different result of the drag force. And then, okay, Okay. And then you look at here, the same person conducting the experiment of drag force versus the diameter of having different density, and here having different viscosity, and so on. They have many variables that they have conducted, that they have to do the experiment, right, to verify and to validate their experiment, to validate their theory here. So it is very huge data that they have conducted, and one person spent about 2 years to complete all these experiment, because he has the 100 data that he gonna plot in these Excel sheets, right? So and then come one person. Alright, and then here he explained that come one person, person B name to the company, and then he plot the dimensionless analysis FD versus rho V squared D squared against the rho VD over mu, and then he conducted one single experiment that can cover the whole the 2 years of experiment. Alright, so here it mentions that that person B only conducted 2 days of experiment. That is experiment can cover the whole experiment conducted by person A. So that is actually the power of dimensionless analysis, because dimensionless analysis they are using because this theory using the ratio. All right. So for example, if they have the different diameter, they adjust the ratio, they can fully utilize this graph. However, if you look at this graph, you can see FD versus D, they are not using the ratio. So when they are not using the ratio, they will miss certain parameter. So the ratio here is very important for the unity result. So that means the dimensionless analysis that can combine 100 data into one single graph, because one single graph using the ratio. Okay. I hope that after this you try to look at this video, because I cannot share the sounds. Okay. All right. All right, class. So here is the similitude study. All right. Basically, the similitude study is mean by the similar. All right. The similar is the study of predicting prototype condition from the model observation. That means from the model, they manage to predict what happened to the prototype condition. All right. Here. Alright, here is the motivations of dimensionless analysis. As I mentioned before, one person conducting the experiment, and then they found that the pressure drop across this cylinder depends on velocity, the density, viscosity, diameter, as well as the height. So they plot many graphs. All right, the pressure drop versus velocity with different diameter, pressure drop versus velocity with different height, and so many. However, if we use the dimensional analysis, we only we can plot only one single graph that can cover the whole of the graph. Right, that is the power of dimensionless analysis. Because you can see here in dimensional analysis, we have all the parameter embedded in one single graph. We have the pressure drop, we have density, we have velocity squared, we have height, diameter, we have all combinations of Reynolds number here. So in single graph, can be used in all application. That is actually the power of dimensional analysis here. Alright, this is what we call to reduce the number of experiment. For example, one person A conducting hundreds of experiment. However, using the dimensional analysis, they can only conduct only one experiment that can cover the whole application because they are using the ratio H over D. Alright, if you have the H, you can use the ratio of diameter, you will get the data here. Alright, if you have the velocity, just plot the variable of velocity and then you can get all the data here. Alright, this is the review of the dimension. Remember that every formula or every unit have the dimension. So what is the dimension? The dimension we are referred to the MLT system, which is mass, length, and time. Alright, you can see the force. The force referred to mass time acceleration. So mass refer to capital M for the dimension. Acceleration refer to length over time squared. So length is capital L over T squared. So here is the ideal gas equation. Pressure equal to rho RT. So when you analyze here, basically pressure have the same unit with rho RT. The dimension of pressure equal to the dimension on the right hand side. So how they prove? They prove by using the dimension analysis here. RT, and then you move the density to the left side, and then you prove here it become L squared over T squared for both sides here. So here no additional dimension. Basically, this is the summary of all the dimension analysis for the length. All right, I would like to share with you the length the symbol is L. The dimension is L. The time, the symbol is small t, and then the dimension is capital T. And the mass, which is M, the dimension is capital M. Remember that the dimension always using the capital, right? So the force is a derived physical quantity. So it derived from the mass. It derived from the acceleration. So here it becomes ml over t squared, and the rest will follow. All right, this is bulk modulus. This is the dimension. This is surface tension. This is the dimension. All right. Okay, so previously we learned in the tutorial how to solve the Buckingham pi theorem. In this lecture, I would like to recap back. All right. Normally, here you can see here x1 is how we write the equation. I believe that you entire of your life you have seen this in many equations. For example, the equations of linear y equal to mx plus c. Another equation, y equal to ax squared plus bx plus c. Remember the quadratic equation. So this is basically the general equation, all right, by using this Buckingham pi theorem. So xy refer to dependent variable. Why we call as dependent? because x1 depends on the function of x2, x3, x4, and so on. Here inside the bracket is the independent variable. It is not depend at all in any variable. X2 is independent. Alright. So that's here the pi term refer to the number of pi, the number of group. For example here, the pi term, if we have 4 pi term, that means pi term number 1 should be placed at the dependent, and pi term number 2 placed at inside the independent variable. This is pi 1 equal to the function of pi 2, pi 3, and so on. Okay. Alright, this is the procedure of solving the Buckingham pi theorem. Alright, I think I don't want to explain this because this is a lengthy of word. It is better for me to explain in the tutorial, because in the tutorial we explain step by step. Alright, I explain to you step by step on how to select the repeating variable, the rules of selecting the repeating variable, alright, the number of pi group, alright. So this is actually the example. Remember that the last class I explained about the solving the Buckingham pi theorem. We form the pi group, and then we select the repeating variable, and then we equate with MLT system. We find the A, B, and C, and then we form the pi term group, right? So let's take a look of this, right? Okay, for those haven't looked at my recording video, please do so. It is very easy. You go to your e-learning, sign in, and then you go to your course, for example, okay, and then you look at, I have posted the video, for example, website tutorial question 6. Okay, you go here. Okay, you go here, people.utm. So, are you managed to look at here? Okay, this is the tutorial question that I have designed for you. Right? This is chapter 4. Okay. Tutorial question. Okay, this is chapter 6. You go here. All right. I would like to show you the video. I think you can see the screen. Hey. Okay, this is the video that I explained about the Buckingham pi theorem. Okay. Can you hear the voice, everyone?
No, sir, there's no audio output.
Okay, there is no audio output. It's okay. Okay, let's take a look on this. Okay, here the question is, the rise of liquid in the capillary tube is to be studied. It is anticipated that the rise H will depend on the surface tension sigma, the tube diameter d, liquid specific weight gamma, and the angle beta of attachment between the liquid and tube. Write the functional form of the dimensionless variable. So the first step, okay, we need to understand the rule first on selecting the repeating variable. All right, the first rule, please remember that selecting repeating variable cannot be unitless dimension. That means we cannot select the angle, the drag coefficient. All this is not the repeating variable because they don't have any dimension. All right, angle. There is no dimension of angle. The friction coefficient don't have any dimension. So we cannot select the repeating variable. Number two, the second terms of dimension cannot be same. For example, when we select the length, the second one repeating variable, we select the diameter. Length and diameter having the same dimension. So we cannot select the same dimension in the same repeating variable. Number three, select independent variable only. All right. When we want to select the repeating variable, select inside the bracket. For example, H, K, and L. We shall not select the depending variable. Number four, the second terms of repeating variable cannot similar dimension. I believe this one, point number four, have the same meaning with point number two. Because, for example, x1 having the dimension m over l, x2 having the dimension m t over l. So m over l having the same dimension. All right. And in addition to that, I would like to stress here, point number five is that all the repeating variable should have MLT, should have three basic dimension, should have M, should have L, should have T, and then it will complete the repeating variable. The difficult part is selecting the repeating variable. The rest would be easy. Okay, so here the step number one is we need to form the function. The question asked here, all right, the rise. That means the rise h is a dependent variable. The dependent variable should be on the left side, which is h equal to the functions of, this is what they discovered, the surface tension, the diameter of tube, the liquid specific weight rho g, and the angle of attachment, right? So based on this is step number one. We need to form the function. Okay. So after we form the function, all right, please expand all the variable into the dimension form. For example, h, the dimension of h is L. The dimension of sigma is m over t squared. How do I get here? It is from the table 6.1. All right. In the table 6.1, you can see the sigma here. Where's the sigma? Here, the surface tension is m over t squared. The diameter is L and the gamma here is m over L squared t squared. All right. So during your test, all right, you can refer this table on your own. All right. Because the test is open book. You can open all the table to refer the dimension analysis table. So for those quite fast on this, you can actually derive this form. The sigma is equal to something, and then finally you will get this m over t. However, during the test, you might feel you want to hurry up on something. So it is better you prepare beforehand before the test, because during the test you can straight away apply the table, right? It can save a lot of your time. And D here with this. After we go to step number one, all right, step number two, we need to find the number of pi. Remember, we have pi 1, pi 2, pi 3. If we have so many pi, we'll have so many calculation. All right. How to get the number of pi? The number of pi, the formula is very simple. N minus m. What is n? N is the total variable. How many n here? 1, 2, 3, 4, and 5. So 5 minus m. M is the number of dimension. What is our dimension here? We have M, we have L, and we have T. 3 only. So 5 minus 3. You can see here, we have 2 pi group, or we have 2 pi terms. Pi 1 refer to the dependent variable, and the pi 2 refer to the independent variable. Okay, so far you guys clear on this? Anyone? Please comment. Are you clear? All right. Okay, thank you very much. Okay, so let's proceed. Step number 3. This is very critical. All right. Step number 3 is selecting the repeating variable. Why we call as a repeating variable? Because that variable will repeat themselves in every pi term. In pi 1 and pi 2 will have the same repeating variable, right? Here is the ground rule on selecting the repeating variable. The repeating variable cannot be unitless. That is the rule number 1. Cannot be unitless. So beta we cancel out. Second one, here, okay, we have the sigma, we have the diameter, and then we have the gamma here. Okay. So between here, all right, we can select. All right, make sure our selection of repeating variable shall consist all the MLT. If don't have M, it will not complete. If don't have T, will not complete. So it should be contain the 3 dimension M, L, and T. So first, we can select sigma. So sigma have M and have T. All right. So sigma don't have the L, so it is not complete. So how to select? So we have to select the diameter, because diameter have the length to complete the repeating variable analysis. All right. So if we select the sigma and diameter, it will help us complete the analysis. So why we cannot select the gamma here? You can see the dimension of gamma is m over L squared T squared. So m over T squared having the same with the sigma here, m over T squared. So it is break the rule number 4, all right, mt squared. So we cancel out. So we only take the sigma and d only, because this is enough to form the repeating variable. Okay. So sigma is, we kill the sigma. So our selecting repeating variable is sigma, all right, and diameter. Okay. Yes, repetitive. Okay, something that repetitive is a repeating variable. So step number 4, we form the pi term number 1. We write pi 1 equal to sigma. This is repeating variable. Sigma, the power of A, diameter, the power of B, and we multiply with the rise of capillary tube, which is H. Remember that we must multiply with dependent variable. Our dependent variable is H. So in the dependent variable, you don't have any power. Don't write any power of C. Just be like this. And then from here, you need to expand what is the sigma in the dimension of sigma, which is m t the power of -2, the power of A. Outside of the bracket, the power of A. And the diameter is length, the power of B. And the height is L. So from here, step number 5, please equate with the MLT system, the power of 0. Okay, once you equate, you can get the value of A and B. How to get here? Okay. A, you can see we start with M. M the power of A, which is A. We don't have any A. So A directly equal to 0. And B here, we have L, the power of B, plus L, which is the power of 1. That is why B plus 1 equal to 0. Straight away, we got B equal to -1. So you can skip T because the T also get the value of A, which is 0. So the pi 1 here refer to sigma dH, the power of A, the power of B. Remember, the power of A is 0 and the power of B is -1. So you rearrange the equation, you will get H over diameter. That is pi number 1. All right. So in this part, this is the special case. You see that we have the angle here, beta. The beta is the dimensionless, don't have any unit at all. So the beta will form their own pi term. We call as a pi term number 3. Even though here we refer to only 2 pi term. But the beta here is dimensionless. It will form their own pi term. So we call as a pi term number 3. Okay. So the second one, the second pi term here, after we select the value of H, and then we need to select the value of gamma. Remember previously we select H, and then here we select gamma, and finally it will lead to the MLT system. We got the pi term to be, okay, the pi term number 2 to be gamma diameter squared over sigma. I hope you understand, yeah, this analysis, it is basically the same. And remember that the one that I explained to you, the pi term number 3, there is a pi term number 3, all right, which is beta only, which is unitless, don't have any dimension. We call as a beta. So the beta will form their own pi term, right? Like their own company will have their own business. So pi term number 3 is just a beta, simple as that. Okay. So far you guys understand on how to solve the Buckingham pi theorem. Can you? Okay. Thank you very much. If you have any question, feel free to use the raise hand button here, right? So after this, please look at the video and then try to digest the lecture here. All right. So it is very simple. For this version, you can see it is the same that I explained. But the one that I explained is full of step by step and it is easy for you to understand. Rather like this, it is only short versions of explanation. Alright. So please look at the video. I have explained well on how to answering this part. Okay. Okay. Next, we proceed with the similitude. Alright. So in this similitude, remember that similitude is predicting the prototype condition. So with the model condition, please comment there. What do you understand with the prototype? What's the difference between prototype and model? What do you know? What the difference between the prototype and the model? I would like to know your understandings of these things. What is prototype? What is the model? What's the difference? Anyone? Amirul Hakim, Eugene, Laos. What's the difference? What is prototype? Have you heard before? What is prototype? What is the model? Huh. Anyone? What's the prototype? What's the model? What's the difference? If you don't understand, please comment there. I do not know. I don't know. If you know, please comment. I want to see your basic understanding. What is the model? What do you know about the model? What do you know about the prototype? Okay. Prototype is a testing to see if final work. If final work, I think this is the fragment sentence. Can you? I can't understand. Prototype is a testing to see if final work. To see of final work. Okay. Anyone? Okay. If you can Google, you can get straight away the solution, the answer. However, the one that I'm going to explain to you a bit different. What is model? What is prototype? Okay. I would like to share with you the prototype and the model. Let me open my file. Currently, I'm doing my research. May I know, have you done your final year project or currently doing your final year project? Please comment there. Wait for a while, yeah. Let me open. This is quite interesting. Okay. Okay. This is tutorial number 2. Okay, let me open. Okay, thank you very much. Okay, I want to show you very interesting things. Okay. Okay, the one that I showed to you, this is the application. Any one of you ever heard about CFD? Computational Fluid Dynamic, CFD? Anyone? If you haven't heard, please comment no. Computational Fluid Dynamic, CFD. No. Okay. Okay, go ZG. Yes, Doctor. Okay, Lim. So what's the application that you normally know about the CFD? Christopher, what's the application that you normally ever heard about CFD? Okay, CFD is a computational fluid dynamic, right? CFD is computational fluid dynamic, right? It is application to visualize the flow, all right? For those, okay, this is basically the application. It is the same with application. Okay, if you want to study on your, if you want to investigate something, for example, import, you want to import. I know you know about the 3D model, right? You know how to design the model by using the CAD software. For example, like SolidWorks. And anyone here know how to design the model, the 3D model? What normally you use? Are you using the SolidWorks? Anyone? Okay, good. Anyone using Katya? Do you know Katya? Okay, Abdul Rahman use NX8, Tinkercad. Anyone? AutoCAD? AutoCAD can use can make the 3D model. Okay, yes. For that kind of thing, we call as the CAD design, computer aided design, all right, to produce the 3D model. Okay, the 3D model can be presented in the drawing. However, those kind of model, for example, you can see GrabCAD. Okay, you search the website GrabCAD, you can see a lot of free model that you can download. Right? For example, like this. Okay, can you see? We have the motorcycle model, we have the car. All right, this is we call the model. Okay, we have the truck, we have the jigs. Okay, for example, we want to model the car, super sport car. Okay. Okay, this is the car. You can get straight away the model. Okay, this is the model. So you can see it gives you in the different format. For example, SolidWorks, step file, this is in Katya. All right. Okay. So this model can be further simulate and analysis. This is the very interesting part if you learn the fluid mechanic. Okay, this is basically the application of fluid mechanic. So, for example, this is my model. This is X. This is the format, parasolid formats, X underscore T. You drag here. Okay, just drag and drop. Wait for a while. Okay, this is the best part that I can say to you if you use this kind of software, CFD. Right? For those want to do the CFD analysis, if you are interested in fluid mechanics, you want to learn more on the CFD, you can feel free to contact me, or I can be your supervisor for your FYP, because this is a this is an important parts in order to simulate the flow. Okay, you can see here loading file XT formats. Okay. Okay, wait for a while ya. So, may I know, have any one of you you are not taking yet your FYP, right? So, are you in year 3 right now? You guys in year 3? Anyone? Year 2. Okay. So, most in year 2. Okay, Amirul answer for all. Okay, thank you. Okay, it's okay. This take time. Let me proceed further. Okay. Basically, the model is where you design, is in a simple way. The model is where you design by using your CAD tool. For example, like AutoCAD, like SolidWorks or CATIA, that you produce the model, right? So the prototype is where you print the model. For example, you create based on your based on your model. For example, you design a car in your CAD tool, and then you create the car, we call as a real things. So that's we call the prototype. Okay, so here all the similitude, how to guarantee your model having the similar with your prototype. So we call as a similitude. So for example, if you want to study the drag force of your prototype, you can conduct in your model system. So based on your model system, it can predict what is the drag force on your real things, on your prototypes. Okay, so here the common dimensionless parameter for the relationship between the pressure drop. All right, remember the pressure drop is a dependent variable. with the function of characteristic length, the characteristic velocity, density, viscosity, gravity, surface tension, the speed of sounds, angular frequency, omega. This can be expressed in terms of the change of pressure, the pressure drop equal to the function of L, velocity, density, mu, gravity, speed of sounds, angular frequency, and sigma. So after we use the pi theorem, we form this function. All right. This is what we previously used, the Buckingham pi theorem, and finally it gives this output in terms of this function. This is dimensionless, don't have any dimension because this is only the ratio. So based on this one, you use the Buckingham pi theorem, it will form the final output in this one. Remember that this first is the pi term number 1 with the function of pi term number 2, number 3, number 4, 5, and 6. So pi term number 1 is the pressure drop, rho, the change of delta P over rho V squared equal to this function. Okay. However, this pi term, you can see this one, delta P over rho V squared is actually referred to different number. We call as a Euler number. Have any one of you heard about Reynolds number? Can any one of you comment? Have you? Okay, Amirul comment. Can SolidWorks do CFD too? Okay, SolidWorks, in my understanding, SolidWorks can do the multi-body dynamic finite element method. So SolidWorks also can do the CFD, but the accuracy is very low. So when you look at the software, you have to understand the accuracy because you want to make sure the accuracy of your model is high compared to the SolidWorks. The SolidWorks only work for creating the 3D model. It gives the better result. However, if you want to do the CFD analysis, you can use other software. My advice, you can use the ANSYS Fluent, you can use the SC Flow, SC Stream. Okay. Okay, so any one of you have heard about Reynolds number. So basically, the Reynolds number coming from the dimensionless analysis. So here you can see where's the Reynolds number. Reynolds number is rho VL over mu. This term, this is referred to Reynolds number. This term refer to Euler number. And this term refer to fruit number. This we call as a fruit, like a buah. Fruit, we call, the pronouns is fruits. This is a France people name it FR, fruits number. Okay, why this fruit number? You can see V squared over LG. Why this one V over square root LG? Because the fruit number, they square root the fruit number, they will get this one. The V squared cancel and the denominator become the square root. They square root everything. Okay, once you square root the pi, it gives the same, the dimension, the same dimension. The square root will not affect the dimension. So here they square root this term, it leads to the V over square root LG. This term, length omega over V refer to Stoffel number ST. And this part refer to Weber number. Okay. How this form? Basically, it form from this one. Okay. 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 So common dimension. So based on the Euler number, we know that Euler number is delta P over rho V squared. Reynolds number is V rho L over mu and so on. So this number we can relate with the force ratio, the two force ratio. All right. Namely, we have the pressure force, which is pressure force is equal to pressure times area. So area we call as length multiplied with length, which is L squared. The initial force, which is we know that F equal to ma. So finally lead to this term. The viscous force tau A, and finally lead to this term. The gravity force mg. So mass is a density multiplied with the volume. So volume is L cube. So density multiplied with L cube is the mass multiplied with gravity lead to this term. Compressibility, the bulk modulus multiplied with area. You got this term. The centrifugal force lead to this form. And finally, the surface tension lead to this form. Based on this part, it form the ratio. Because you see the Euler number. Previously, the Euler number is delta P. Delta P here directly related to the pressure force. That's why the pressure versus initial force. We look at back the Euler number at the denominator. Rho V squared. The initial force is, you can see rho V squared. However, we have the L squared. Remember that L squared cancel with L squared. We got the rho P over rho V squared. So in simple way, we can explain that Euler number is directly related to the pressure force over the initial force. The Reynolds number relates to the initial force over viscous force. The Fruit number refer to the initial force over gravity force. The Mach number relates to the initial force over compressibility force. The Stoffel number refer to the centrifugal force over initial force. And lastly, the Weber number relates to the initial force over surface tension force. Okay. Any one of you here okay so far? Are you clear on this? The two forces. Okay, still okay. Basically, this is the first is the definition. You need to know the definition first. Okay. The Euler number is this, and then you know that the Euler number directly related to the pressure force over initial force. Now you see that this number all have the initial force, initial force, initial force, initial force. Alright, the only difference is the pressure here, the viscous, the gravity, the compressibility, centrifugal, then surface tension. So we can say that the Euler number influenced by the pressure force. The Reynolds number influenced by viscous force, viscous effect. The Fruit number influenced by gravity. The Mach number influenced by compressibility. Stoffel number influenced by centrifugal. And lastly, the Weber number influenced by surface tension. That's it. Very simple. So you can see here, I explained before, Euler number, flow is dominated by pressure drop. The Renault number influenced by viscous effect. The Froude number influenced by gravity. The Mach number influenced by compressibility. The Stoffel number relate to the omega here, which is repeated itself periodically. And the Weber number is surface tension. Okay. So this is where you learn about similitude to study the predicting the prototype condition from the model observation. For example, if you want to do the prototype, you want to investigate from the model. Of course, you want to create the car. For example, you want to create the airplane. First, before you create the huge airplane, you must draw in the CAD tool. You must draw, you must design. So once you design, you need to calculate, you need to do analysis. So analysis, you analyze from the model and then you can predict what happened to the prototype. So that means similitude is where you make sure your model having the similar pattern with the prototype. Okay. Okay, this is a very huge file. Okay. So in order to make sure your model and your prototype having the same similitude, okay, the first, you have to make sure that having the geometric similarity. For example, the length ratio is constant between all corresponding points. Example like this here. Okay, this is your model and this is your prototype. This is you try to design the keyboard. This is your model. And then this is your prototype. Okay. This is length of the model. This is length of the prototype. The geometric similarity means the length of the model over the length of the prototype is constant. Okay, for example, your constant is 3, the number of 3. So this is, for example, this is L, this is Y. Ym, this is Yp. Okay, the Ym divide with Yp, what's the answer? The answer still the same, the C. So that means the ratio of the scale here, the length scale here, Lm over Lp is the same with the Ym over Yp. Okay, are you guys clear? So now you understand what is a geometric similarity. The length of the model over the length of the prototype is equal to the Y of the model over Y of the prototype. So this is we call the geometric similarity. However, for example, the angle here. Is it applied to the angle of the model and angle of the prototype? Is it apply or not apply? Angle. Okay, angle should be the same. Okay, if you having different angle, for example, this is the prototype is 3 times bigger. For example, Ym equal to 3 PC, Lm equal to 3 LP. The angle should be the same. Angle model shall be the same with angle of prototype. Why? Because angle don't have any dimension. Remember, what's the angle of dimension? No, unitless. Dimensionless, no dimension. What's the dimension of y? What is the dimension of y? What is the dimension of L? Do we have this dimension? What's the dimension of y? What is the dimension of L? The length. Anyone please comment what is the dimension? L. Okay, what's the dimension of theta? I mean, what's the dimension of angle? Dimensionless. So, in here, there is no dimension of angle. So, it is not applied to the ratio of angle, the ratio of dimensionless. It applied to the ratio of dimension, the linear dimension, which is length with length, y with y. Okay, that's all. So, secondly, the kinematic similarity, right? The velocity ratio is constant between all corresponding points. Okay, the second, in order to make sure that your model have the same similarity with the prototype, second one, kinematic similarity. Okay. What's the kinematic similarity? For example, this is the model, this is the prototype. Okay, this is, for example, this is the ball. This is the prototype ball. The flow in this direction. Okay. Okay. For example, you measure the velocity here. Okay, and then you measure the velocity here. Okay. For example, you measure suddenly become 3 meter per seconds. What do you think of the prototype velocity? Please comment. I want to see your logic thinking. Anyone? This is the model. This is the cylinder, the flow from the left to the right. And then you pick one point, you measure the model velocity at this point, and then the prototype velocity at this point. And then you discover that the velocity of the model here is 3 meters per second, and here is, what do you think? Okay, anyone? Okay. Anyone who say the same? Different? Please answer same or different. Different or same? Okay, why okay. Okay. Why you say different or why you say higher? Please explain. In this way, in this lecture, explain velocity ratio is constant between all corresponding points. Okay. What do you think? Why it is different? Is it not same? Okay, so the answer is, refer back to this slide. The kinematic similarity means the velocity ratio is constant, not is same. Okay, it is different. Constant and same is different, yeah. Velocity ratio means velocity model over velocity of prototype is constant. between all corresponding points. For example, velocity ratio Vm over Vp is 2 times. So what is a Vp? Of course, Vp is 3. Okay, this is not right here. Let me delete here. Okay, Vm over Vp is ratio dia 0.5. Okay, it is constant. Okay, so what is the velocity of prototype? Anyone please calculate? What is the velocity of prototype when the velocity ratio is 0.5? Anyone? Okay, 6. Why? Because you substitute the value of here 3, and finally you will get the Vp here is 6 meter per second. This is just example only. Okay, for example, you calculate the velocity here is 9 meter per second. What's the velocity here? Velocity of prototype. Okay, correct, Christopher King. Okay, here it mentioned that the velocity ratio is constant for the corresponding point. So this corresponding point refer to this point. This corresponding point refer to this corresponding point. You cannot use this point with this point. This point, okay, this point shall be referred to this corresponding point. This point shall be referred to this point. That's why we call as a corresponding point. And having the velocity ratio. This 3, this is 6, multiply with 2. This is 9, multiply with 2, which is 18. Are you clear so far? What is meant by kinematic similarity? Okay. Here mean you can see velocity ratio is constant, not velocity ratio is same. So mean the constant, for example, the constant is 0.5. So the entire velocity ratio is constant 0.5. So between all corresponding point, the corresponding point is here. If you refer to this, the corresponding here, here, and here, that is called corresponding point. Okay. And last but not least, similitude shall have dimensionless perimeter. Okay, this one is very important that we're going to go further. Euler number. Remember that our common dimensionless perimeter, Euler number, Renault number, Fruit number, Mach number, Stoffel number, and Weber number. So what it means here is okay, what it means here is this is model, this is prototype. The Euler number, the common dimensionless is the same. Euler number of the model and Euler number of the prototype is the same. Or Renault number of the model and Renault number for the prototype is the same when the dominant effect is significant. Okay, that is what it means. Okay, in order to make sure similarity, 3 things. The geometric similarity, same, that I explained previously. The geometric means the ratio the dimension, linear dimension ratio is constant. Okay, for example, L over Lm over L prototype is constant. The mass ratio here, actually this is a velocity, all right? This is typo. Velocity ratio of the corresponding fluid element is constant, and the common dimensionless parameter below should be equal. Okay, that I explained here. The Euler number of model equal to Euler number of prototype. Reynolds number of model equal to Reynolds number of prototype. Okay, that is why you need to learn this. Okay. Other dimensionless parameter, for example, the drag force. The drag force divide with drag force, it is dimensionless. Alright, the initial force divide with initial force is dimensionless. This is explained. This is the extended of dimensionless. Okay, the power input, for example, the dimensionless of power input, the power input of the model divide with the power input of the prototype is dimensionless. Okay. So in this part, you only learn similitude in three conditions. Okay, let me open up the the course information. Okay, let me open up the course information. Okay, you can see here, you are going in week 12. In this week, you're going to learn the confined flow, free surface flow, and Reynolds number flow. Height Reynolds number 3. Only 3 conditions: confined flow, free surface flow, and height Reynolds number flow. Okay, this that I can explain here, confined flow is the flow has no free surface. What it means by free surface, like this. This is water. For example, in today's news, we have a flood in Johor. May I know any one of you, Manji, flooding at your area? Are you okay? Flooding? Are you okay with current situation? Are your area affected with the flooding? Is your area so far so good? Okay, Amirul, Hakim. Yeah. Okay, no problem. Okay. If you have problem, you need to report immediately. My area not okay because currently I'm stranded. Actually, my area at Pulau Jaya, but now I'm at Terengganu. I'm stranded here because in this yesterday news, there is the blockage now between Kuantan to Kuala Lumpur. There is a flooding in highway, so I cannot travel. So now I'm stranded at Terengganu. I cannot travel back to Johor. So I'm waiting for the flight to recede. Okay. So for those yang having a problem, so I'm having a problem. I'm stranded now at Terengganu. I want to go back. I cannot. So okay. So here, this is the flooding. For example, I show you the flooding. Okay. Okay. This is the water. Okay. This is the water. So you can see that the water here, this layer, okay, we call as a free surface area. Free surface. Okay, free surface area. Because this area is free from the water behind here. This water have a molecule of water. Okay. And you see this free surface, there is also molecule. But this molecule of water is free from the other side. So you can see we have the air. Okay, this water molecule attract. Okay. This water molecule attracted by bonded with the other molecule. So this is free from the other side. So you can see it is free from the air. So that's why we call it as a free surface area. Okay, so far you guys understand what you mean by free surface? There is the separations between the water and air. Are you okay with this? What is a free surface? Okay, I think my application unable to run. It is heavy. Okay, so the confined flow is a flow that has no free surface. That means the flow is fully 100% of fluid, 100% of liquid, no combination of liquid and gas. Alright, so what we can say that when you involve of confined flow, the dominant effect is viscosity. So what's the common dimensionless that affect the viscosity? Anyone? What are the parameter here, dimensionless parameter, that affect that dominant on the viscosity? Is it Euler number? Is it the Reynolds number, Fruit number, Mach number, Stropher number, or Weber number? What the dominant effect shows here with the viscosity? Is it the Weber number that shows the significant effect with the viscosity? Okay, you look at here. You can see dominant effect is viscosity. So when the question give you the situation, the flow is in confined flow, that means the dominant effect is viscosity in incompressible confined flow. So what's the parameter here involve viscosity? Can you find what's the parameter involve viscosity? Please look at the viscosity term. Correct. Reynolds number, not the Mach number. The Mach number relate to the speed of sounds. So when the question asks in the confined flow, you must equate the Reynolds number. Very simple. So you can see, I read the question. A test to be performed on a proposed design for the large pump. The large pump is a prototype that to deliver 1.5 meter cubic per second of water from 400 millimeter diameter impeller with the pressure rise of 400 kilopascal. This is the prototype, the real things. Now, they talk about a model. A model with 80 millimeter compared to 400 millimeter diameter impeller to be used. What flow rate? This is the flow rate of the model and the pressure rise to be expected. So now they said that this is incompressible. You know that the incompressible mean in the water. Okay. Okay, for similarity to exist, so now the question give you two things, the model and the prototype. So in order to make sure similarity or similitude, they should have a similarity in dimensionless parameter, which is Reynolds number. You can see that the model fluid is water. Water is incompressible at the same temperature as the water in the prototype. Okay, so here for similarity to exist in a confined incompressible flow, Reynolds number must be equal because this is dominant with the Reynolds number. You can see here, dominant effect is discussed in incompressible confined flow. Okay, there is no on the free surface. So you know that the pump, okay, let me tell you. This is the pump. Okay, this is the pump. Okay, for example, this is centrifugal pump. Okay, this is the blade. Okay, and then the water from here go here, and then this water 100%. This is confined flow. There is no free surface. So 100% filled with water. This 100% filled with water in the pump. So it is involved of the confined. Confined means confined here. Completely full of water. Incompressible. This is water. Water H2O is incompressible. Alright. So when the water is incompressible under this confined area, confined space, the dominant effect is viscosity. So the dominant effect is viscosity directly related to Reynolds number. Okay. So here we mentioned that confined flow. So of course, inside the pump, there is a 100% of water. It is confined to the incompressible flow. So the dominant effect is Reynolds number. Reynolds number must be equal. You can see that Reynolds number of the model equal to Reynolds number of the prototype. And Vm here, this is the expansion of Reynolds number. Reynolds number is equal to Vd over nu. Okay, nu is kinematic viscosity. Okay. And second, this one I will explain more in the tutorial, don't worry. The second one is the free surface flow. What is the free surface flow? The one that I explained to you. Okay, we have the surface of water. The top side is the air. So in this free surface, the dominant effect is gravity. Okay, what's the dimensionless parameter that affect the gravity? Which one? Which one have the gravity? Please find which number that relate to the gravity. Anyone? Fruit number. You can see the fruit number related to gravity. There is no dimension other than fruit number related to gravity. You can see Weber don't have gravity. Euler number don't have gravity. Only the fruit number, which is Fr equal to V over square root Lg. Okay. This gravity is dominant in the free surface flow. Okay. That's why they equate here fruit number of the model equal to fruit number of the prototype. Okay, this one I will explain to you. This one, the question asks, this scale model of the surface vessel is used to test the influence of proposed design on the wave drag. The wave drag force, this is the drag force, is measured at the model speed of 2.44 meter per second. What speed corresponds to the prototype? And what wave drag is predicted from the prototype? Neglect the viscous effect. Assume that the model having the same fit with the prototype. Okay, now you can see the scale model of a surface vessel. So this is in between the surface. So the dominant here is the gravity. So that the gravity, you are going to use the Froude number. Okay. And lastly, this will explain to you in the tutorial, don't worry. Is the height Reynolds number. You can see in your last height Reynolds number. So what is the height Reynolds number? When you are having very high Reynolds number, that means your flow is compressible flow. So the dominant effect is Mach number. For most compressible flow, which is the air, the Reynolds number is very large. It's very large. For example, like 10,000, 100,000. So it's very large of Reynolds number. So when the Reynolds number is very large, that flow we consider as a compressible flow. Okay, so when the compressible flow, the dimensionless that give the dominant effect is the Mach number. Okay, the Mach number m, which reflect to the velocity of the flow over the speed of sounds at the local location. So Mach number equal to V over C, velocity of that flow of fluid over the speed of sounds. So this is referred to the model equate with the Mach number of the prototype. So and then you explain further. So this one is the similitude problem. You can see here, the pressure rise from the free surface to the nose of the fuselage section of aircraft is measured in the wind tunnel. Okay, with this speed. If the test is to simulate the flight at the elevations of 12 km, what is the prototype velocity and the expected nose pressure rise? So here the solution, you can see the speed is very, very high. This speed is very high, relate to the high Reynolds number. So what's the Reynolds number? Can you type here? What is the Reynolds number formula? The formula of Reynolds number. Anyone? What's the Reynolds number formula? Rho, Reynolds number. Okay, Reynolds number formula. Reynolds number formula is rho VL over mu or VL over nu. Okay. Okay, rho VL over mu. Okay, correct. So, when the velocity here is very, very high, so what happened to the Reynolds number? Is it the same, increase or decrease? If the velocity is very high, is the Reynolds number increase or decrease? Increase. So majority of you say increase because this one is Reynolds number is directly proportional to velocity, or we call as Reynolds number directly proportional to velocity. Highest velocity will give highest Reynolds number. So in this case, you can see the velocity of the wind tunnel speed is 900 kilometer, which is very, very high. So high velocity will give the high Reynolds number. So this is the case of compressible flow. So most compressible Reynolds number is very large, not significant. So we can use the compressibility flow, the Mach number. Okay. Okay, wait, yeah, I think this is hand. Okay, wait. So that is why you equate here the Mach number of the model equal to the Mach number of prototype. Or in other words, the expansion of Mach number, we know that the expansion of Mach number is equal to V over C. C is the local speed of sounds. Mean the local here is the location at that particular of point. So you know that C here is the square root of K R T. This is the gas constant. K is the specific heat ratio. Specific heat ratio multiplied with the gas constant, and this is the temperature, absolute temperature. Different temperature will have different speed of sounds. So you equate back velocity over square root of K R T. This is constant, this is constant. The only variable is temperature and velocity. So that's why they equate in here. Velocity over square root KRT. Are you okay so far? You guys understand? When the Reynolds number is very high, we shift to the compressibility flow, which is the dominant effect is Mach number. Are you okay, guys, so far? Do you guys understand what's when the velocity is very high, the Reynolds number will go high as well. Okay. So this tutorial I will explain, don't worry. This is periodic flow. Will not cover this. Okay, this one the same. Okay, and tomorrow class, okay, I will cover this one, the last part, normalized differential equation. Right. In the meantime, I will cover the tutorial question. I will record myself solving all kind of flow, compressible flow, the viscosity flow, and different type of flow, and posted to the e-learning. All right. So I hope that you use this opportunity to study. You open up the e-learning and study on your own tutorial, because I only have 2 hours. The tutorial 2 hours. So I cannot explain everything in one time. So I record myself all the tutorial, and please study during your free time. If you don't have any free time, please spare at least 1 hour a day to look at the video, to make a revision on your own. Right? Please discipline yourself. It is very important, especially during work, study at home. Okay. So far, you guys have any question? I hope that you have submitted the assignment, programming assignment. Okay. Do you have any questions so far? Okay, sure. I will send you the slide. Don't worry. And as well as the recording video in the e-learning. Thank you, Lee, for reminding me. Okay, sure. Thank you very much. Thank you for your time. See you soon. I end my session with okay, tak sempat scan. It's okay. Saya perasan Amirul lambat sikit masuk. Okay. Okay. This is 22. I think Amirul 21. Okay. Please scan. For those done, please comment. We have done. Okay, thank you very much. It's okay. Maybe tomorrow I will explain to you the software. This is a very interesting software about the CFD, computer fluid dynamic. It is a fun. You can play around with the fluid flow, what happened to the car when the flow around the car. You can see the color contour plot. This is fun when you want to do the final year project. So I think that's all for now. Thank you very much for your time and listening. Assalamualaikum warahmatullahi wabarakatuh. Bye everyone.
Waalaikumsalam. Thank you, sir.
Thank you.